All right, everybody, welcome. Welcome on in. Welcome to the second half of the course. So you're halfway there. Um, we got 3 more weeks of working on this stuff, and then hopefully you finish successfully, and then you don't have to worry about this anymore. So, couple things to talk about here at the top of the class. So I want to just kind of give a rundown of how the second half's going to run, because it seems like, oh, half a class, but it's 3 weeks and we're done. In fact, sort of less than 3 weeks, since we're on a Tuesday here. Here's where we're at. So first I want to talk about the exam. So unfortunately, there are a number of people that have legitimate reasons for why they were not able to take the test last week, which means I'm going to have to extend that test window. So, here's the situation. It's how you learn anything in life, right? You try something, you don't do it perfectly, you make some mistakes, and you try it again better after that. So that's what you're all doing in this class, right? You try to do stuff, you make some mistakes, you learn from it, and then you do better the next time. We in mathematics are trying to combat cheating in online math classes, right? Because it's not really fair. I've taught classes where I give an online test, and I can see all these people that spend an hour and a half taking the test. They get a B or a C or whatever, and then there'll be like 8 people who took the test in 5 minutes and got 100%, right? Because they're using apps to take the test instead of actually doing it. Most of you who are, put in the effort to try to do it right. And we can't really have that as teachers. We can't really have classes that people are getting through without learning material, and they're just cheating their way through. And it's not really fair to the students who are putting in the work. For a student to put in a ton of work and get a B or a C, and then some other student who puts in no work and gets an A, we can't have classes like that. It's just, it doesn't work, right? So one of the things we're trying to do is combat that by having proctored exams. I learned, this is the first time I tried it, and I learned a few things that I can do better next time to make things a little bit smoother for people. But a number of people had legitimate reasons why they tried to take the test and were not able to, so I'm extending that test. I'm not thrilled about doing that, because it's kind of not fair to the people who got in there and took it last week, but it's also not fair to the people who legitimately tried to get the test taken but were unable to, for various reasons. There's like 3 or 4 really good reasons that categories that people fell into for not getting it done. So here's the deal. You can take the test this week, and that's it. So make your appointment with the testing center. I sent out a Canvas announcement with some details that you'll want to know when you're setting up that appointment. The main thing to keep in mind is that the testing center is being remodeled this week. So depending on what day you go, the testing center will be moved to the LRC 128 or 129. So if you go to school and the testing center's all, they're putting new windows and stuff like that in there and you can't get in there, then go to LRC 129. The LRC, the Learning Resource Center, is the nice building in the middle of campus. It's 3 stories tall. It's nice building. Go in there and ask around, see if you can find 128 or 129. That's where they're going to be having the testing center this week. Okay, I know there are a couple of people who sorry, I lost my train of thought when I was reading something, reading one of the comments. So there were a number of people who were having issues with getting in there during the day. That's another thing I hadn't really thought out ahead of time, apparently, is that some people work 9 to 5, and it's really difficult for some people to get excused from work. So if there's anyone who needs a evening appointment, I can go to campus and sort of proctor a test in the evening for whatever group of people need that. But you need to contact me immediately. I'm not going to set that up unless there's a need for it. Some people mentioned needing it, but haven't gotten back to me about actually doing something about it. So if no one lets me know, I'm not going to set up an evening proctored on time to come in and take the test on campus. If people get a hold of me, I'll set something up for later this week. So don't wait on that, because we can't really do it last minute, because I have to let everyone know. So contact me immediately if that's you. Otherwise, you can set up your tests through the testing center. Still need your Scantron, ID, all that kind of stuff. But look for LRC 128 or 129 if you're taking your test later in the week. Okay, so that will be your last chance. So please get that taken care of and set up in order to do that. Let's see, there's a question here. Are the exam grades you have entered into XYZ homework the official grades for those that did take the exam thus far? Right, those should be your grades. So here's what I did, so there were 17 questions on the test, right? No, whoops, this is sorry, getting my classes mixed up. This is the class where we had 13 questions on the test for this class. Nope. Sorry, someone wrote that they were in Math V44, which is statistics, so I'm getting my stacks mixed up here. This is the Calc one, and we had 13 questions, right? So nope, that's right. Sorry, that test kept confusing me because they wrote they were taking statistics, which I'm not teaching. 17 questions. So there were yeah, that's what I said originally, what I thought. There were 17 questions on the exam. And I took, what I did, I believe, I took the top 3. So I took the top 3 scores and I averaged them. And that is the total possible. So I think that came down to, was it 14 or something like that? So anyways, you could say there was a slight curve to the exam, right? So basically, there's actually a couple people that got above 100% because they scored above those. If you got the top score in the class, you got slightly above 100%. So that gave everyone a little bit of, leeway room, and ended up being what looked like a decent curve to the test. A lot of people were able to pass. So, okay, so that's where we're at with that. And if you're wondering why I can't pull up the grade sheet right now because I don't want to expose anybody's grades. But I believe that's how it was. It was something like out of 14 or something like that. So if you're wondering, that's why there was a slight curve on there. Oh, and when you're looking in the XYZ homework, please keep in mind that is not your grade for the course. The XYZ homework, the only thing that's in the XYZ homework is the homework and the test, which is 80% of your grade, so it's most of it. It'll give you a good idea of where you are, but it's only the homework and the exams factored in, not that third category, which will get factored in at the end of the semester. Okay? So, yeah, any questions about any of that? No, we're good. Okay, if you're someone who's going to try to take that test this week, make sure you take care of that immediately or get a hold of me with questions immediately so we can you can make sure you take advantage of that and don't miss again. If you miss the week this time, then there's not much reason why you couldn't get it done in 2 weeks, okay? Okay, so where are we going from here? Let's pull up the XYZ homework. I changed the homework date. So I was looking at them, and originally the homework 4 was due like tomorrow, and I thought that wasn't quite enough time. Again, you shouldn't be waiting until the homework is due in order to do it. You hopefully are getting it done ahead of time, or you're going to find yourself very crunched in that last week of school. It's going to be very stressful and unpleasant. So try to stay ahead if you can. My goal, it's possible we're going to get through all of Chapter 4 today, and then we'll start talking about Chapter 5. My goal is to kind of start Chapter 5 Thursday, finish it on Tuesday. Oh, no, wait. Actually, it may take us 3 to 4 class sessions to talk about Chapter 5. Chapter 4 is a little bit lighter. Let's see. There's a question. So the total weight is not your grade for the class. That's right. It's 80% of your grade is factored into that. The other score won't exist until the end of the semester, till the end of the class. Okay. So Chapter 4 is really light. I think most of you, by doing the homework and watching the videos and paying attention today, are going to do fine with Chapter 4. I'm not saying it's easy or you'll get it immediately, but I think it's doable, right? I think it's pretty reasonable. Chapter 5 is a very heavy chapter. There's a lot going on there. It's kind of a return to some, and it might even be more challenging than some of you found those early chapters where we talked about limits and derivatives. It depends. Some people just get limits immediately. Some people are confused by them always. But most people find chapter 5 to be fairly challenging. Okay, and there's a lot to it. So we're going to move through chapter 4 fairly quickly because I think you'll all largely be okay. Chapter 5, we're going to slow way down. We're probably going to take at least 3 days to cover chapter 5, and it might even spill over into a 4th day. And chapter 6, I don't have a ton of videos for. We're going to talk about it mostly in class, so we'll probably take a couple days to do that. But if you notice, I don't really want to be covering a lot of material here on the 27th because, first of all, half of you have already taken your test by that point. The homework is due the next day. That doesn't give you a lot of time to work on it. So really my goal is to start talking about chapter 6 and kind of be done with that the Tuesday of week 6, which means we won't really have much to even talk about on the last day of class. Which, you might go, why would we have a class where there's not that much to talk about? But the problem is you don't want me covering new material the day before it's due and after you've already maybe taken a test on that material, right? So my goal is to get through chapter 4 today. We'll start chapter 5. Depending on when we finish chapter 5, we'll dive into chapter 6 and hopefully get that done well before that due date of that last day of class. And then that last Thursday, maybe we can just, you can ask me questions or however it is that we decide we should do that, depending on where people are at with things. But some of you might be done with the course by that Thursday, right? If you've already taken the test, you've finished up your homework, you might not even be around that day. So it just kind of depends on where you're at with the class. And I think this is the class where there were a couple requests for more late passes, so I just kind of reset everyone's late passes. So I think you all have 20 again. But if you need, let me know. I can put out more late passes for you. Okay, so that's kind of where we're at with things. That's where we're going in the next few weeks. If there's any questions, let me know. But we're going to dive into it. So like I mentioned, we're largely going to talk today about logarithms and exponentials and the derivatives of those things. So there's some videos in here. You've got I'm going to go over it today, but if you still have questions, there's a Professor Leonard video here. We've got logarithms where I go over the basics of logarithms in general. Those are confusing, but we'll go over them today. But there's some videos I made for that. And then there's the derivatives of logs and exponentials, and we'll be talking about that today as well. So we're going to get to all those topics today, talk about all those things. I know that probably seems like a lot, but the truth is we don't go really, really deep with logs and exponentials in this class. It's important to know how to take the basic derivatives of logarithms and exponentials, but we don't do any kind of fancy stuff with it in here. If you take the engineering calculus course, you do some brutal problems with logs and exponentials. But in a business type calculus class, the problems are not nearly as difficult as you find in the engineering calc. So that's good news. We don't have to do real fancy stuff. I'm not saying every problem is going to be easy, but they're the kind of things where once you kind of see how it's working, you can keep applying it to other problems, and the stuff comes out pretty well. So that's where we're going. And then as you can see, when we get into here, this chapter 5 on integration, really heavy. Antiderivatives, not too bad, but there's a lot in there. Substitution, that's one that it's kind of like the chain rule where people struggle with that a bit. It takes a while to wrap your brain around it. The definite integral is a whole thing, right? That takes a while, it's a whole kind of seems like a separate topic, not really related to what we're doing. It is. The fundamental theorem of calculus takes a lot of topics from this whole course and ties them together. And then integration by parts is something that, by and large people don't find particularly fun. So you've kind of got in chapter 5, 1, 2, 3, 4, 5 huge topics. Whereas what we're doing here, I think there's, in the homework, I think there's 4 sections, but each one of them is not incredibly complicated. So that's why we're doing a whole chapter today. And then coming up, we'll probably be doing like 2 sections a day, something like that for a bit. And then when we get down to that last chapter. Okay? So that's where we're headed. So with that, let's dive into some stuff. For 4.1, let me blow this up so you can see what I'm talking about. 4.1 exponential functions and 4.2 natural logarithmic functions. This is stuff that theoretically you've seen already, right? That's like what we'd call prerequisite material. That's stuff that you saw in an algebra class, or hopefully saw in an algebra class somewhere along the way. And that, look, it's totally reasonable if you forgot the logarithms and you go, oh, I remember when I was a sophomore in high school, we did logarithms, but that was, 8 years ago. That's totally reasonable, but it's stuff you saw at one point, hopefully, and are a little bit familiar with. So we get to, and I'll review those things today, so you don't have to worry about it too much. But we've got exponential functions, logarithmic functions. Then basically we're going to look at how do you take the derivatives of those things. And the derivatives are not that complicated. You have to remember your chain rules and your power rules and your product rules and all that kind of stuff. So you're going to have those kind of problems mixed in to the homework set. But it's just like the derivative problems you've been doing, except now every once in a while part of the problem will be a logarithm, and you'll go, oh yeah, I have to use that logarithm rule. Or it'll be an exponential, and you go, oh yeah, I have to use that exponential rule, or whatever, and you go from there. Okay? So that's what we're looking at today. That's what we're discussing. So with that said, let's jump into it. And we can look at some particular homework problems along the way. Most of the problems for number 1, or for section number 1, are mostly plugging things into exponential functions and evaluating them. So as long as you're comfortable with, say, a TI-84, then it would be really easy. Maybe you've got, you could technically do these things by hand if you needed to, but a nice graphing calculator will be very helpful in this scenario. Right. So let's talk about exponential functions. And I'll be jumping back and forth. I like showing the book because they kind of outline stuff very well, but then I want to jump into, we'll break away and I will expand. We're not just going to straight read the book all day, but I'll show you some stuff of what's going on. So here we have the definition of the exponential function. The exponential function is a function that can be written in the form b to the x, where b is greater than 0 and b is not equal to 1, and x is a variable. We call this an exponential function. Now there's a lot of kind of conditions on this problem, but they're important. So b has to be greater than 0, because if b is not greater than 0, if it's negative, you start getting this weird oscillating behavior and the points bounce around and they don't become helpful. These exponential functions show up all over the place. No matter what area of research or anything that you want to go into, business, economics, biology, all of that, you're going to see exponential functions describing behavior. And so we want to make sure that we're limiting ourselves to those really, really useful functions. And to do that, we have to make b greater than 0, right? Those of you who are going to, say, become mathematicians, then down the road, you may study those other kind of functions, but they're very, very rarely used. So we're sticking to the ones where b is greater than 0. Yeah, there's a question. Yeah, unfortunately, we're not going to be able to do retakes on exam 1. There's just already kind of enough going on with the tests. But if you're concerned about a test score, feel free to talk to me, and we can sort of have a discussion about your grade and your place in the class and stuff like that. Okay. And b also cannot be equal to 1, because if b is equal to 1, you just get the line y equals 1. It's a very boring function and isn't particularly useful. Not in the kind of setting that we're talking about anyways. So, right. Now, here's one place where people get very confused, is the difference between, say, the difference between these two functions right here. See, we have 2 to the x and x squared. In fact, I'm going to put it one page down so there's less interference here. So 2 to the x versus x squared. People get these confused. One of these is a polynomial, and one of these is an exponential function. So kind of think about that definition that we just described and try to figure out which of these is a polynomial and which of these is an exponential. Well, one of these has 2, which is a specific number as a base, and the other one has it as the exponent. And one of these has a variable as the base, and the other one has it as an exponent. This first one, 2 to the x, that fits our definition for an exponential function. And this one, x squared, well, you've already dealt with x squared. You're used to that, right? You've been dealing with polynomials through college algebra and stuff like that. So you just want to pay attention to which one of these has a specified determined base and a variable exponent, and which of them has a variable base and a specified determined exponent. And that's how you're going to tell the difference between if you're dealing with a polynomial versus an exponential function. So sometimes students will mix these two up, but you don't want to, because the way you take the derivative of x squared is not the same way you take the derivative of 2 to the x. They are very different functions, and they have very different derivatives. You already know how to take the derivative of x squared. That's going to be 2x, right? But you don't know how to take the derivative of 2 to the x. You might go, well, can't I apply the same rule? So we bring the x down in front, and then we subtract 1 from the exponent, and the answer is no. It doesn't work that way. Okay, so that's kind of piece number 1. Make sure you can tell the difference between 2 to the x and x squared. Oops, that's not what I wanted to do. I wanted to do this, okay? So that's what we're talking about when we talk about an exponential function. So that b could be 2, it could be 3, it could be 7. Let's take a look at things in Desmos. So we're talking about things that look like 2 to the x, things like this. Here's 2 to the x. We could have a different base. Here's 3 to the x. Here's 9 to the x. And you're starting to see a pattern, right? You're starting to see some familiarities between these different exponential functions. And the answer is yeah. There's some overall behavior that describes all of these things that is convenient. So notice what happens is there's a horizontal asymptote here at the x-axis. And then as soon as these x values go positive, they just start shooting up towards infinity, just incredibly fast. The exponential function is one of the fastest growing functions. It grows very, very quickly, very quickly. So, and that's why it can describe things like population growth, the number of bacteria in a petri dish as they grow over the course of a day. It can describe things like compound interest. It can describe, anytime you have something growing by a certain percentage per time unit, you can describe it with this kind of exponential behavior. Excuse me, I'm going to have to go get a water here in a minute. I'll talk for a little bit more, and then I'll go grab a water. So we have this exponential function. We could notice our specification was that b had to be greater than 0. So we can get a situation where b is a fraction as long as it's greater than 0. For instance, 0.5 to the x. And we get a similar but opposite behavior here. So we're going to save that. I'm going to talk about that in a minute. because I think if we first understand these kinds of graphs, then it's real easy to understand the other ones. Also, I would like to point out that the transformations we worked with earlier in the semester hold for these functions as well. So if you want to do a shift left, right, up, down, all that kind of stuff, flip it upside down, all those transformations still hold, okay, in the same way that you would expect them to. So it's nice because they're very predictable. Okay, very predictable. So you'll notice that these graphs get steeper as the base gets bigger. And there's a reason for that. That's because if something is doubling each time a step is taken, well, that's pretty fast growth. But if it's increasing by 9 times each time a step is taken, that one's going to grow faster, right? So basically the green graph grows faster than the other ones, but they're all growing pretty quickly, okay? So let's understand some basic patterns because you're going to need these for some of the homework problems. So let's look here. It looks like they're all going through the point 0, 1. Now, why would that be? Well, if we think about it, the 0, the x value, that's what we plug into here for x in our exponent, right? Let me make this bigger here. So what happens when you raise anything to the 0 exponent? You get 1, right? The one weird case is 0 to the 0, and that actually depends on what kind of math you're doing. But in this class, we will never have to worry about 0 to the 0. So any other number you take to the 0 power, you're left with 1. So what does that mean? For any base, if you plug in 0 for x, you're left with 1. That's why all of the exponential functions go through the point 0, 1. Okay, all of these. Notice all of these. If we just make up another one, 13 to the x, okay, I predict it's going to go through that point. Yep, went right through that point. Why? Because if you raise 13 to the 0 power, you get 1. Right? It wasn't really much of a prediction. We knew from mathematically that's what's going to happen. So let me clean this up, make it a little easier to look at. So we've got our basic exponential curve here so that as soon as it goes into positive x territory, it just starts shooting up. At 0, it goes through the point 0, 1. And then over here, it's leveling off towards the x-axis. Now, why is it doing that? Well, if you think about it, over here, we're plugging in negative x values, right? So if you think about it, we're plugging in things like, let me do this. Say, take for example, 2 to the x, and we want to plug in negative 5. That means we're really considering 2 to the negative 5. Where did it go? We're really considering 2 to the negative 5, but what's 2 to the negative 5? The negative means you bring it to the denominator of a fraction, so that's going to be equals the fraction 1 over 2 to the 5. Right? So that becomes 1 over 2 to the 5th. But 2 to the 5th is what? 32? 2, 4, 8, 16, 32. So that equals the fraction 1 over 32. So you can see those numbers get really small, and that's only at negative 5. So imagine when we're at negative 100 or negative a billion or negative a trillion. Those numbers are getting very, very tiny. So that's why it looks like they level off and become the x-axis, but they don't. It's approaching it asymptotically towards a horizontal asymptote. So they're getting forever closer and closer to the x-axis, but never quite touching it, right? It never quite gets there. So that's why we get this kind of behavior. And if you saw a minute ago where I made this instead of 2, let's make it 0.5, so we make it some fraction, the whole behavior is just flipped around. So you can see over on the right side, we're getting that asymptotic behavior for the same reasoning, except it's switched because 0.5 to a negative exponent is actually going to flip that up to the numerator. And then we're going to have, our numbers are going to get bigger. So that's why you're getting this shooting up towards infinity on the left, going through 0, 1 as always, and then leveling off on the right. right? That's the behavior that we're getting. But most of the time, you'll be dealing with things like this, 2 to the x, right? That's sort of the standard that you'll run across much more. So let's see. What about domain and range? So by looking at the graph here, we should be able to determine the domain and range for this function. So I'm going to give you just a few seconds. Look at this and see if you can ask yourself, what's the domain of this function? What's the range of this function? In fact, I'm going to give you a second to think about it while I go get a water, because I'm getting dehydrated here. So I'll be right back. Okay, sorry about that. This room I'm in is getting warm. I'm getting dehydrated. It's making me kind of drowsy. Oh, that water's helping. Okay. So we can determine the domain and range by looking at this. So remember, the domain is the x values that are covered by this function. Well, it looks like we could put any x value we want in here, and it looks like that's going to correspond to a y value on our graph. So the domain for these exponential functions is negative infinity to positive infinity. It's anything on the x-axis, right? Because if you zoom out far enough, you'll see, pick any x value you want, that's the x value of a point on this graph. So what about the y values? What about the range? The range is all the y values. Well, it doesn't look like any of our points have negative y values. This whole area down here, totally wasted. There's no points down there. So our exponential functions do not have any negative y values. But they do have positive y values. So it looks like the range goes from 0 to infinity. And that's 0 with a round bracket because it doesn't include 0, right? There's no point on our exponential function that has a y value of 0, but you can get as close as you want to 0. Right? There's a y value of 0.00000000001, right? That's going to exist somewhere, but not 0 itself. So 0 to infinity for the range, negative infinity to infinity for the domain. All right, let me catch my place. Where are we here? Oh, here we go. The number e. So we talked about different bases that we can use for our exponential function. You saw me use a few of them. We had 2 to the x, 3 to the x, 9 to the x. Well, there's a very special number called e. And you see this if you're looking at a TI-84 calculator in front of you. It's got there's some buttons that have a lowercase e on it, right? And you'll see this thing come up from time to time. And you've probably seen it in algebra, and we told you to use it, but you're kind of like, where does this number come from? And the answer is, to come up with the number e, you have to use calculus. That's why we could never really explain that number to you before. We could show you how to use it, but when someone would ask, who came up with that? Where did that number come from? The answer is you need calculus for it, right? Yeah, so there's a question that came up. Yes, there will be a practice exam for the final exam. That's right. The final exam will not be Scantron. It will be written, so you'll get partial credit. You'll have a practice exam for it, all that kind of stuff. Okay, so you know, you can look at that number e. You can look it up. It's 2.718281828459045, and it goes on, right? It's an irrational number. It has an infinite, non-repeating decimal expansion. It's like pi, right? Why do we always write pi with a symbol? Because if you try to write it as a decimal, you never get to stop because it goes on forever and it doesn't repeat. There's some numbers that repeat, like 3.333333333 forever. So we have a nice way of shortening that. You put like 3.3 and you put a bar over the 3 to show it's repeating. With the irrational numbers, you can't do that because there's no repeating. Like the digits will repeat, but not in that same pattern, right? Like you can see here, the number 4 comes up, but not in the same pattern the whole time through. So that's why we come up with symbols to represent irrational numbers, because writing them in decimal form is sort of a fool's errand, right? Once you start, you can never stop if you want to do it accurately. But there's a pattern that comes up in mathematics, and it's the pattern of 1 plus 1 over x raised to the x. This comes up in a lot of different areas. So people said, well, what if we take this? What if we take the limit as x goes to infinity of 1 plus 1 over x raised to the x? Now, I know when you first see that, you're like, well, who would care about something like that? Why is that important? Well, it's a property that is very important in mathematics, and early mathematicians figured out that was really important. So they said, what happens if we send x to infinity? Because they knew if they could figure out what that number was, it has some very convenient properties, and I mean very convenient. So they did that, and we are using the limit here. That's why we need calculus. If you take the limit as x goes to infinity of 1 plus 1 over x raised to the x, you get this number e. And you can actually kind of work on it using the limit. I like the way we do limits. So you've got your 1 plus 1 over x raised to the x, and then we send x bigger and bigger like it's in a limit. So we plug in 1, 5, 1,000, 10,000, 50,000, 100,000, and you can see the number is settling down because it's asymptotic. It's going up and approaching this number, and the number it's approaching, that y-asymptote, is e. Okay, so that's where that number e came from in mathematics, and it's very useful. Like most of you, hopefully at this point, very comfortable taking derivatives of polynomials. When you see a problem where you have to take the derivative of a polynomial, you're like, great, this is easy. I know how to do that. Derivatives with exponentials can be even easier than that. So sometimes they're even easier than polynomials, which is one reason they are desirable to use in certain situations. So we've got that. So E, remember, is approximately 2.71828, blah, blah, blah. So we can use it as the base for an exponential function. Oops, these are both red. Let's not do that. Let's make one blue. Okay, so you can see the red one is 2 to the x. The blue one is e to the x. It makes sense they're pretty similar because, remember, e is 2.7 something. Right? So it's a little bit, it should be kind of between 2 to the x and 3 to the x. Oops, that one's blue again. Let's make this one say orange. And you can see, sure enough, e to the x is kind of located in between the orange and the red one. Right? It's kind of falling in between there. So we can often, oops, that's not what I want to do. We can often just look at e to the x, and this is a very convenient function to work with. So this is e to the x. A lot of times you're going to use that when you have an exponential to deal with. It's, as I say, very convenient. Oops, where did my book go? Here it is. Let's see, we looked at that. Okay, so then we have graphs of the general natural exponential function. So with the number e as the base, we have the very important and useful general exponential function f of x equals a0 e to the kx. Many of you have probably seen this function in your chemistry class. You've probably seen it in a math class. You may have seen it in other classes. In chemistry, sometimes they call it PE to the RT. They're just using different variables, but it's the same idea. It's exponential growth. But for chemicals, you may have seen it in your biology class when you're talking about, okay, if we start off with this many bacteria in a petri dish, we let them grow. How many do we end up with later? You're looking at this. You may have seen this in the context of continuous compounding for interest-bearing accounts. You'll see this function. So this function shows up all over the place. Super, super helpful. Very, very easy to take certain behavior and capture them with this. So here's the thing. We could look at population growth using this function that we have right here. But we can also use this to do exponential decay. So as something decays. So what's the difference there? Well, if we have a population, they tend to grow exponentially. Not as steep as what we saw. They don't double usually every generation or anything, but they grow, maybe by a few percent each generation. And it can be captured with this formula right here. So what is a decay? Well, the easiest way to give you an example of decay is, say, radioactive decay. What happens when you have radioactive material is you have elements where the nucleus is very large, and you have these different forces that are taking place inside the nucleus of an atom. Basically, things are repelling each other because all the protons have positive charge. Positive charges are repelling each other. But then you have this strong nuclear force, which once things are very, very close together, they sort of try to glue together. They try to stick together. But that nucleus gets so big that some of the protons are far enough away that they're only really repelling each other. So it becomes very unstable. And what happens is these, say, uranium or plutonium or something like that, they have these big, huge nucleuses that are unstable. And every once in a while, one will just break apart. And all the protons and neutrons go shooting in the different directions, hopefully not into you. And oftentimes running into other, say, uranium. And then if one of those neutrons happens to hit another nucleus that's already unstable, that could be enough to make that one break apart. And then now you have a whole bunch of more parts shooting, and then they hit other atoms that take those already unstable nucleus and break them apart. So this kind of decay can happen in an exponential manner. Right? This is why you don't want to be near them. You don't want those protons and neutrons traveling through your body at a high rate of speed. They can mess up your DNA and cause, problems. And this is what essentially a nuclear explosion is, whether that's happening in, say, a nuclear bomb, or that's what's happening in the sun. You have these atoms that are breaking apart, and then they're hitting other atoms that are so close to them, they're guaranteed to hit these other atoms, and then breaking those apart. Those break more apart, and this all happens in just basically in an instant, and it releases a huge amount of energy. So if your K is positive here, that's called your growth rate. If your K in this formula is positive, you're going to have a growth problem, right? It's going to be, and by problem, I mean the problem that you're working on is growth. So you're going to have an exponential growth. So bacteria growing, populations growing, interest growing, something like that. Whereas down here, if you have a negative growth rate, then you're talking about something shrinking. So when those uranium atoms break apart, they break into other things now because they have less protons and neutrons, and they go towards things like lead, right? Eventually becoming like a bunch of lead. So that rate then is how much uranium you have. The amount of uranium you have is shrinking over time. Okay, so that's how you get a decay problem, or a decay rate, is that the amount of uranium left, say, is decreasing over time. Okay. This A sub 0, that's your initial amount. So that's whatever you started with. So up here it would be your starting population. Down here it might be the starting amount of uranium that you have. Okay. E is the number we already looked at. We know what that is. K is your growth rate given in the problem in some way, and T is the amount of time. Okay, so t is time. And these things, you know, the TI-84 is very good at dealing with exponential functions. It even has a little button for e to the x, so you can calculate that rather easily. I think we talked about all these, except exponential functions are continuous. We kind of saw that when we were looking at them. They're continuous functions. So let's take a look at so this initial section, basically what you're doing is you're just taking values and you're plugging them into an exponential function and then getting some value, so that you're not even really manipulating that much. So let's look at this problem just so you can kind of see. Here's an exponential growth problem. So imagine that at a particular time, a kitchen counter has on it 5 bacteria, and this type of bacteria doubles in number every 10 minutes. That's one thing about bacteria. They reproduce very quickly, right? This is why you leave, you know, with humans, obviously it takes many, many years to have the next generation. But with bacteria, you leave some soup on the counter overnight, and it gets in that, they call it the danger zone, where it's a certain temperature where bacteria like to reproduce. And all of a sudden, you get up in the morning, and the soup's gone bad because the bacteria, each bacteria is reproducing every 10 minutes. So you start with, say you start with 1 bacteria, 10 minutes later you have 2. 10 minutes later you have 4. 10 minutes later you have 8. 10 minutes later, you have 16. So you can see how this exponential growth gets very big very quickly, right? So the bacteria doubles every 10 minutes. The exponential function, here they give you the function, so that's great. They're giving us a function, is a good model for predicting the number of bacteria A of t in the population t minutes from some particular start time. How many bacteria could be predicted to be on the counter 2 hours later? Now here's, again, I mentioned, maybe that was in the morning class. But units are very important, right? You may have taken math or science classes where your teachers are kind of on your case about not writing out units. And you're like, well, I wrote the number, but without the units, it doesn't really mean anything, right? Paying attention to units can be very helpful. Not only because it helps you understand the problem, but you can catch mistakes. So what some people would do here is take 2 and plug it into this function. Except what's the problem with that? Well, we are told that this function tells us about the population t minutes from some particular start time. But the question we were asked is in hours. So you wouldn't plug 2 into this function. You would say, well, how many minutes is there in 2 hours? Oh, there's 120 minutes, and you would plug that into the function. So by paying attention to those units, you recognize, oh, I should be doing everything in terms of minutes, not in terms of hours. And that's the kind of mistake that, gets made. So you want to be careful here. But then that's the kind of problems that you're going to do. Once you figure out it's 120 minutes, you just go, oh, I plug 120 in here, and then you get your answer. There's about 20,468 bacteria. And see how they sum it up with a nice, concise sentence? If there are initially 5 bacteria on the counter and the population of bacteria doubles every 10 minutes, then after 2 hours, there will be about 20,468 bacteria on the counter. That sums it all up. We know exactly what we're talking about there, right? Here's another setting. So we were just looking at bacterial growth. Here's another one. Some sociologists found that this exponential function, where p ranges from 1 to 10, is produced when members of a discussion group of 10 people are ranked according to the number of times each participated. So N1 represents the number of times the first ranked person participated, and N of P represents the number of times the pth ranked person participated. So, there's these different functions. There's so many different functions that we can capture with exponential behavior. So, again, all we're doing in this problem is essentially taking a value from the problem, plugging it into the function, and then seeing what we get. So nothing too tricky there. Okay, here I talked about interest a number of times. Here we have an interest problem. So let's look at that. When a particular amount of money P, called the principal, is invested at the interest rate R and is compounded n times a year, the amount A accumulated after T years is the following. So that might sound like a lot. P is your principal. Principal is the amount of money that you start with. Okay. R is your interest rate being written as a decimal. So remember, like 5% in decimal form is 0.05. 50% would be 0.5, right? N is the number of compoundings a year. T is the number of times of year. So if some of you are not familiar with continuous compounding, it's actually very powerful and you should be familiar with it, because there are times in life when it's going to work for you and times in life where it's going to work against you. So here's how it works. Let's say that you have an account. So the way a bank works is I say, hey, I'm going to help you keep your money safe. And you go, great. That's good, because no one will steal it then. So you come to my bank, you put the money in my bank, and then we kind of think of it as like sitting there in the vault. There's this vault with all this money in it, and that's not how it works. I mean, there's some money in the vault, but the money, if I'm the banker, the money that you give me is not sitting on a counter somewhere. I'm using that money to make more money, right? And you know, this is a discussion that happens large. On a larger level, where, you know, sometimes people think that maybe there's things that are being done that are unethical with that. That's sort of a conversation for a different day, but we'll sort of keep this simple and say, I'm the bank, I've got money. What am I going to do with the money that you give me to hold on to? Well, I lend it to other people. So someone might come in and say, hey, I need to take out a loan for a home. And I say, okay, I'll give you a bank loan for your home at 7%. So I round up a bunch of the money in the bank and I give someone, say, $700,000 so that they can go buy a house. And then they pay me 7% interest. And then I go to all the people whose money that I'm using and I pay them 1%. So that means I get to keep the 6% that I'm getting paid. I get to just keep that. So it's really your money that's being used to buy this other person's house, but me sitting in the middle as the banker, I get to keep all that money, right? Like, good luck trying to find an account right now that pays more than 1 or 2%. And yet if you go try to take out a loan for a home, you're going to be paying 6, 7%. Where'd all of that extra money go? It went to the bank. They get to keep it all. Oh, so there's a question in the chat. So someone's from my morning class. The problem is the morning class and the afternoon class are different courses. This is a applied calculus class, whereas the morning class is college algebra. So to my student who's asking, if it won't really help you with the class that you missed this morning. If you go to the YouTube channel, though, it's recorded there in the playlist, and you could watch that. That would be more helpful to you. Okay, so that's how interest works, right? Is basically I pay you to let me have your money, and then other people pay me even more money to borrow that money from me, and I act as an intermediary. Okay, that's how interest works. So the thing is, you can have a 5%. Let's make this easy, that you're not going to get anywhere near this, but just to make the numbers easy to understand, let's say there's a 12% loan. So you put some money in the bank and I say, hey, I'll pay you 12%. So we wait a year, and at the end of 1 year, I give you 12% interest on your money, which would be huge. You're not getting 12, even historically 12% is hard to get, but now you're lucky to get 1 or 2%. Well, what if you had $10,000 in the bank most of the year, and then right at the end you pulled out most of the money because you needed it, and then I just said, well, you only have $1,000 in the bank now. I'm only giving you 12% on that. That'd be kind of messed up, right? So there's a number of flaws with interest being compounded once a year. That is, once a year I give you the payment of the interest. So it tends to, that's why some accounts, if you go in, like, you get what's called a CD or certain types of accounts that banks have, you can't just take the money out when you want. You get a higher interest rate. You might be able to get 3% on what's called a CD, but there's rules that say you can't take it out until a certain date. And they'll have certain dates where you can come on like 4 times a year and take your money out. Otherwise, if you take the money out early, you get a huge penalty on the interest. And they basically pay you very little. So that's why, it's money that you don't really need. And I'm not going to use this money for a year. I'll put it in this other account and get a higher interest rate. But I know I'm not allowed to touch it until it's accrued the interest that it needs. Well, what if instead of paying the interest once a year, we paid it once a month? So instead of getting paid 12% over the course of a year, what if I gave you 1% each month? And most of the time people go, okay, yeah, well, that should be the same, right? And the answer is no. You're better off getting 1% a month than you are getting 12% a year, which sounds silly at first until you think of it this way. Let's say on the first day of the year, you put some money in an account. And I've decided that I'm going to pay you monthly your interest. So at the end of January, I pay you some interest. Well, that means in February, you're earning interest on that first interest payment, right? So at the end of February, you're getting interest on the original money you put in there. You're also earning interest on your first interest payment. And then at the end of February, you get another interest payment. So then at the end of March, you're getting interest on that principal, but also on your interest payment from January, your interest payment from February, and it goes on like this. So you're essentially earning interest on your interest. So that's why the more times you compound in this kind of scenario, the better you do, right? Now, there's sort of a sweet spot for this, right? Where if you increase the number of compoundings, you'll always make more, but you reach a point where it gets a little bit, it doesn't really help that much. Like, once you go past monthly, you might go, man, well, monthly means I'm only getting 12 compoundings a year. What about daily? Could I get compounding daily? And a lot of banks compound daily, although they cheat you out of 5 days of the year. There's the bank holidays. Even though they get paid interest if you have a loan to them, they still charge interest on those days. They don't pay you interest. I took an actuary exam where we had to study how banks work, and it's always in their favor. Like, whichever side you're on, the bank always rounds in their favor. But the bottom line is you might go, well, 360 or 365, if we want to keep this simple, compoundings per year, well, that should be way more money, right? And it turns out you only make a little bit more than if you compound monthly. Like with monthly, you can make a lot more money than compounding once a year, but it's called diminishing returns. You still gain, but your returns don't gain by as much. And you could take this to the extreme and go, what if I compound every minute? What about every second? What if I compound 1,000,000 times a second? And the answer is you just start gaining like pennies. You'll get a few pennies more. So you've got your basic problems where they're going to have you do this, where you compound, say, like in this one, what did they say? Determine the amount accumulated after 15 years if $2,000 is invested in an account that pays 8% interest compounded quarterly. So quarterly means fourths, right? So quarterly means you get 4 compoundings a year, just like there's 4 quarters in a dollar. So that's where the 4 comes from. The 0.08 is the 8%. 15 is the number of years, and 2,000 is your original interest. So you do that, you get 6,562. So that's not bad. You turned your $2,000 into 6,500, but that's because you didn't touch it for 15 years, right? This is why sort of you get this is one level of inequity in society, right? Is people who have money they don't need are able to put their money in accounts that just sit there and gain money, right? You don't even have to work for it. Your money just becomes more money. Whereas people who have less money, you don't have $100,000 to just sit around and put in an account and have it make money for you, right? So it's why it's difficult sometimes. But if you have extra money sitting around, you can make it grow. This is also the argument for, you'll hear a lot of people, and I know it's really hard, but a lot of people will tell you that you should start saving for retirement in your 20s, and they're right. The problem is most of us when we were in our 20s, very poor, right? It's hard to come up with money to put aside. I was in graduate school. You make very little money when you're in graduate school. It's hard to put money away for retirement. But if you can, that money, if you think about it, if you started a retirement account at age 21, that money has like 45 years to grow before you retire. Whereas if you wait until you're 40 to start saving for retirement, that money now only has 25 years to grow. So a lot of times people think about it as like, oh, saving for retirement, that's like a thing that old people do. No, that's a thing young people should do. The problem is the way our society currently works. When you're in your 20s, you don't usually have any money to put aside. But if you can, even if you can just put it aside like $100 a month in your 20s, it will make it a lot easier when you go to like start saving for retirement. Like, you know, say in your 30s or 40s when you start making more money, then you can put more away, but you've lost those decades of saving up. So anyways, that's a sort of how that works. Let me see. Oh, that's a good point. I didn't do attendance yet. I will do attendance here in a few minutes. I'm glad that was brought up. It's easy for me to forget when I start focusing on the mathematics, but we'll look at that in a minute. There's another thing called a logistic function, which, as you can see, has sort of an exponential function embedded inside of it. And those look kind of like this. They look more like this, where they come up. They kind of have like a horizontal asymptote, then they come up and have another horizontal asymptote. So some functions behave like that. But again, you're just going to be taking values from the problem and plugging it in to these and seeing what you get and interpreting. That's how most of these are. Just plug stuff in, see what you get. Yeah, is how that section works. Okay, that was a good point. Why don't I take roll before we get to the next section? Where's my pen? Okay. Let me know if I've missed anybody, but it looks like, and I think a few people have dropped, so some of these people aren't around anymore. But the people I'm missing today, Elizabeth B., Samantha C., Isabella G., Christian G., Clarissa H., Armin K., Eduardo R. Ashley V. and David F. So if you're any of those people, throw it in chat so I can get you marked as here. I don't think I mentioned that yet. I didn't do the drops yet that I was talking about doing, but I do plan on doing those. I think I'll get to them tomorrow. I got totally swamped with work this week between my classes and then department chair stuff. The last 7 days has been quite busy. But I will get to those drops tomorrow. I think I'm almost totally caught up on stuff, but I'll get to those drops tomorrow. Okay? All right. With that said, let's move along to logarithms. And logarithms are confusing for people, but it's one of those things where I think it's half notation. The notation is super bad for logarithms, in my opinion, and I think that's half of what confuses students. So if we can get past that. Oh, we got... Okay, I got you, Elizabeth. If you can get past the notation, a lot of these problems are not too bad. At least for the level of stuff that we'll be doing in here, it's not terrible. Okay, so the natural logarithm. When we say the natural logarithm, we're talking about base E logarithms. So it means it's base E. Okay, so remember what we do with, we talked about, well, we know about inverses, right? So inverses undo a function. So if one function doubles a function, its inverse cuts it in half. And a lot of times the reason that we want to use inverses is to ask different questions about the same material. So we could do the following. We could say, like the problem we just did a minute ago, we could take a similar problem and say, what if you wanted to save for retirement and you wanted to have $1 million in your retirement account when you retired? Which sounds like a lot, but when you think about the way retirement money works, it's not, because when you retire, you can't start spending the money in your account. Like, let's say you're used to spending $100,000 a year, right? And then you have $1 million in the bank. Well, when you retire, that's only going to last you 10 years, and then you're out of money, right? So the way you have to do it is you save up enough money that you can live off the interest when you retire. So that's why you need $1 million or more dollars, because you have to live off the interest generated by that $1 million. So that's why you generally have to have more money saved up for retirement than you think, depending on what you're getting from Social Security, which they keep threatening to cut, which wouldn't be good for most people, or if you have a pension or something like that. But that's kind of how you have to plan. So you could say, you could ask the question, okay, like the one we looked at. Okay, what if I put away $2,000 at 5% interest for 30 years, compounded quarterly, all that kind of stuff, right? What could it grow to? But that's not usually how you want to plan for retirement. The way that they usually attack how to plan for retirement is say, how much do you want when you retire? Say, I want $1 million in an account when I retire. Okay, then the question is, how much do you need to start saving today in order to make that work? See how you're asking the question from a different perspective? You're not saying, if I put this amount of money away, how much is it going to be worth later? You're saying, if I want to have this much money later, how much do I have to put away now? And that is flipping the question around, and that usually involves the inverse. The inverse of the exponential is the logarithm. So if we want to ask a question like that, we have to change it around. We have to ask the question differently. So we introduce this thing called the logarithm. And we have a couple different forms here. The natural logarithm in the equation a equals e to the t, the number t that when used as an exponent on the base e produces the number a is called the natural logarithm of a. I don't love this definition of the logarithm. It sounds particularly confusing. But basically what they're saying is, if we start with some amount, what power did I have to raise this e to get it to be a? You're basically asking the exponential question in the other direction. So we write this t equals natural log. So the ln stands for natural log, and the natural log is the inverse of the natural exponential. Okay. So t equals natural log of a if and only if a equals e to the t. Don't like that form. Let's see. Where was they say this is the first form. I can't remember if they use a second. Oh, final form. I don't like either one of those. Let's rewrite this. So generally the way we write this is to say that our definition for the logarithm is that y equals, where's my book? Let me make sure I don't get this backwards. Let me use this algebra book. This makes it a little cleaner. Y equals log base b of x means b to the y equals x. Okay, this is generally how we interpret this. This is the cleanest way to use as the definition. So y equals log base b of x is the same as b to the y equals x. And you might look at this and say, well, isn't that just an exponential? It is, but notice how the x and y have been switched. That's because that's what inverses do. They switch the x and the y values. So we're actually dealing with an exponential, but with the reversed variables. So the role of those variables are reversed. Okay. So if you just learn this definition, you'll be able to do like most of the logarithm problems in this chapter, right? So how would that look? How do we do these kinds of problems? So we say, let's see, they get right into log properties and log equations. So here's some where they say, it's like question 6, where they say, so first of all, they tell you the answers must contain the natural log, so that's fine. But they say convert each exponential equation to the corresponding logarithmic equation. So how would we convert this? Well, we use this definition right here, because we are currently kind of looking at it in the form where it's y equals e to some value. This is kind of a weird way to write that question, actually. I didn't... it's not usually how these problems are stated. Let me see here. So if we have y equals e to the 2x, then our base is e. Our exponent is 2x. No, our exponent is y. This is not the question I was looking for. looking for a different problem. These are a little further along. So let's see. Are we going to have time to cover log properties? Probably. So let's say you have a problem where they're saying, well, we're talking about the natural logarithm. So we'll use ln. The natural log of e to the 5th. Right? Like, how would we simplify something like this? The natural log of e to the 5th. The natural log and our exponent to the 5th, these are inverse functions of each other, so they undo each other, and those would just simplify to be, say, 5. Okay, let's see. They're jumping right into the properties and equations. Okay, usually there's a couple warm-up problems to get to those. So where's the book? So they do some examples here of that one we were just looking at. This is a very non-standard way of approaching this topic, of writing these questions in this way. So convert each exponential equation to the corresponding logarithmic equation. So we've got that. Here's their reasoning. We know that the logarithm is the exponent, and the exponent is 2x. Therefore, we know the logarithm is 2x. So we've got 2x as this logarithm here. The base is e, so we use the natural log. The exponential equation y equals 2 to the x corresponds to the logarithmic equation y equals 2x. Why? Because 2x, they argue, is the logarithm, and or natural log of y is equal to 2x, and the natural log of it's kind of a weird way of writing that. Here's how you would actually, that's actually not a good way of how they express it. Let me see if I can show you a little bit better. Say we've got y equals e to the 2x. Okay. Y equals e to the 2x. Okay, so generally what we would do at this point is we would take the natural log of both sides of the equation. So you would end up with the natural log of y is equal to the natural log of e to the 2x. Okay. So we've got the natural log of y on the left, which is what we saw in the book that they had. But they had 2x on the right, but we have natural log of e to the 2x. But remember, just like up here, the natural log and e are inverse functions and undo each other. So you're just left with the 2x. So the natural log of y is equal to 2x. That's sort of a better way of thinking through the problem. I think what they're doing in the book is trying to give you a way that's easy to remember, but without actually understanding what you're doing. So it's, in my opinion, it's easier to take the natural log of both sides and then try to go through and simplify things from there. Here they're just trying to get you to memorize some procedure, which I don't think is particularly helpful. But there's examples that you can follow along when you get to that point. Evaluate each of the following. So the natural log of e, right, that should just evaluate to 1 because the natural log and e undo each other. Right? They're inverse functions of each other, so they just undo each other. Okay, well, let's get into some properties of the natural logarithm. So the natural log of e is equal to 1. We just kind of argued that. The natural log of 1 is equal to 0. This goes back to, Remember, when you have an inverse function, you're switching the x's and y's from your original function. Well, we looked a little while ago that the exponential function, here, let's look at it. Remember this? We said all exponential functions go through 0, 1. All those exponential functions. Well, let's look at, we've got the inverse. The logarithm, the inverse should be a reflection across that line y equals x, and sure enough it is, the natural log of x. And notice how this goes through the point 1, 0. That's how it works with inverses and functions. If you have a point on this graph, which is 0, 1, then on the inverse, it's going to be the point 1, 0. It flips the x and the y. So that's actually why the natural log of 1 is 0, is because all these natural log graphs go through the point 1, 0. Okay. The natural log of e to the x equals x. We've actually used that a couple times so far in our reasoning. The natural log and the exponential undo each other. Okay. Now here's some that are not immediately obvious. So if you take the natural log of a product, it becomes the sum of the natural logs separately. If you take the natural log of a division, it ends up being the subtraction of the logs. And here we have the power rule that says if we take the natural log of a base to a power, then we can bring that base down in front, the exponent down in front, and manipulate it that way. So let's take a look at some examples of how this works so I can sort of explain. So here we're using that first property, that multiplication property. So they're taking the natural log of 3x and making it the natural log of 3 plus the natural log of x. The natural log of 3 is just a number. If you have your calculator, you can take it out right now and press natural log of 3, enter, and it's going to give you some number. You can't do that with x because x is a variable and your computer isn't going to know what x is represented by. But natural log of 3, people see letters in there and get confused about what that means. Natural log of 3 is just a number, right? Literally put it in a calculator and you'll see it'll tell you about 1.0986 or whatever, right? So that is using rule number 4 up here. Here then they use rule number 5, which is a division. If we take the natural log of a division, which is what we have right here, the natural log of a division, it becomes the subtraction of those two logs. So we can set things, then we can split it apart this way. So it's the natural log of 8x minus the natural log of x plus 4. But now notice what we have. Now notice that this first piece is the natural log of a product, 8 times x. So that's why they split it now using rule number 4 into the natural log of 8 plus the natural log of x. So see how sometimes in these log problems, you have to use more than one of these properties before you finish. So in the beginning, when you're just learning these properties, it's usually just one and done. Use this one property, then you're done. But like here, we can see we have to use 2. You use the division one to change this to a subtraction of logs. Then we look at this and go, oh, hey, that's a product. And we change it to the sum of the logarithms. Okay. Property 6. So see how we have the natural log of x to the 6th? That power rule, that last one, we're looking at rule number 6 right now. This allows you to bring the 6 down in front. So natural log of x to the 6th equals 6 natural log of x. Okay, so that's really handy because this rule right here is kind of the only way we have for getting something out of the exponent. We don't really have any other way to do that, and sometimes you need to. Like, what if you were trying to solve for a variable, but that variable was up here in the exponent? You can't solve for it when it's up in the exponent, so how are you going to get at it? Use the natural log property to get it down in front. Then you can solve for it. We do that all the time when we're dealing with logarithms. Okay, so here's kind of an expanded one. We've got 12,000 times the natural log of xy to the 5th. So notice what we have here. We've got a power going on with the 5th. We've got a product going on with the x and the y. And we've got something out in front multiplying the whole thing. So you're going to have problems where they have you expand these using log properties and condense them using the log properties. And I know they seem weird at first. It just takes a little bit of practice, and you just sort of have to keep looking at those log properties that are on page, what page is this? 330 approximately, and trying to figure out which log property can I throw at this problem. And you do it by looking and going, oh, here's a product, here's a quotient, here's a power rule. You'll get better at recognizing these things. So notice the first thing they did is they took the xy to the fifth and broke it into a sum. Natural log of x plus natural log of y to the fifth. They broke it up separately. So that's property 4. But then this one over here, we can apply the exponent rule to it because it's y to the fifth. So then we bring that 5 down in front. So you'll get used to this. Sometimes they want you to condense the problems. That means write everything with just one single logarithm. But notice how here at the end we have it written as multiple logs. So when they say expand, like what were the directions here? Use the properties of natural logarithm to expand, right? You see that word expand a lot. Expand each logarithmic expression. So they started with a single logarithm, and they fully expanded it out using those properties into multiple logs. You'll sometimes use them here. They'll use the word condense, or they'll say write as a single logarithm. And basically, you start at this end, and you work backwards to the beginning. Right? So for instance, here they say, use the properties of the natural logarithm to write each logarithmic expression as an expression with a single logarithm. So here you're starting with multiple logarithms, and then you're working towards writing it as a single log. So when you're done, you should just have the ln written one time. Right? And that's what they do. They look at this and go, oh, there's a plus there. That's like that rule for product, right? So notice how then they can, actually the first thing they do is recognize there's a 6 here, and they go, oh, that's the power. So they make it y to the 6. That's using that property 6 about the exponent. And then they say, hey, we have a sum of 2 logarithms. We can use that product property, and then they stick it together as a multiplication. So we just used this rule number 6 first, and then we followed it up with rule number 4. And it takes a little practice to get used to those and figuring out how to write them. Okay. But there's examples and videos and stuff on how to make that work. Okay, let's look at this one. To 4 decimal places, approximate the solution to the equation e to the 2x plus 5 equals 12. So this is basically, let's do that separately. This is basically what I showed you how to do a minute ago, where we applied you can see they're applying the natural log to both sides of the equation. That's what we just did. But let's do it where you can actually watch me doing it step by step. So let me write this. E to the 2x plus 5 equals 12. Okay. So how would we go about solving this? So e to the 2x plus 5 equals 12. Okay, where did it go? E to the 2x plus 5 equals 12. How are we going to solve this thing? So for starters, anytime, see how our exponent right here has a variable in it? We ultimately want to solve for x, right? That's our goal in this problem, but it's up in an exponent. How am I supposed to solve for it when it's in an exponent? That's kind of your red flag right there where you go, oh, I'm trying to solve for a variable that's in an exponent. I'm going to need that logarithm property for the powers. That property number 6 that we looked at over here. Where did it go? This one? This is the only way we have for getting something out of the exponent. So that tells me, well, I'm going to need a logarithm then. Because I look at this problem and I go, there's no logarithm here. Well, then introduce the logarithm by taking the logarithm of both sides of the equation. So the natural log of e to the 2x plus 5 equals the natural log of 12. Now, the natural log of 12 is just a number. You could put it in your calculator, but keep in mind, the natural log of 12 is the exact value. When you put natural log of 12 in the calculator and hit enter, it's giving you an approximation. It's approximating it, right? Which is not as desirable, right? When you want to know how to maximize your profit, you don't want it like an approximation for how to maximize your profit. You want to know exactly how to maximize your profit, right? Also, one of the problems with approximations is if you then start using those approximations in more calculations, your little tiny error value, or what you thought was a small error value, can grow, right? There's certain problems that come up in this class with the old book that I used to use, where students would do like a 10-part problem, and they would start approximating on step 1, and by the time they got through part 10, their estimate for what the pricing should be for a certain product would be off by like 15%. Well, if you're pricing your product wrong by 15%, your business might be in trouble, right? So we always like exact values, okay? Now, here's the good news. The natural log and e undo each other. So that means the left side of the equation just becomes 2x plus 5. So 2x plus 5 equals the natural log of 12. So now we just isolate x. So subtract 5. So 2x equals the natural log of 12 minus 5. And then divide everything by 2. And that should be what we got in this problem down here. Yep, that's what we got. Natural log of 12 minus 5 divided by 2. Oh, what's wrong with my fraction bar? Oh, because I never closed this. There we go. X is the natural log of 12 minus 5 over 2. Put that in the wrong spot. So the natural log of 12 minus 5 over 2. That's your exact answer. Now, when you throw it in a calculator, it's going to give you an approximation and say, that's approximately negative 1.2575. Now, approximating, especially in business, is usually fine at the end of a problem, right? When you're all done, you're not going to do any more calculations. Sure, go ahead and round. That's fine, because no one goes to their boss and says, hey, I think we should invest a natural log of $12, right? No one talks like that. That would be silly. You figure out what that comes to in dollars. But again, don't do calculations with rounded numbers, because that little error that seems really small can grow surprisingly large, right? It can be surprising what that grows to. Okay. So that's how you would use the natural log to solve that kind of a problem. Anytime you see a variable and an exponent that you want to solve for, start thinking about using the natural log the way that we just did. All right. Here is an example of what I was talking about earlier. The radioactive isotope uranium-235 decays according to that exponential decay model. A equals A sub 0 e to the negative kt. That's just our decay model that we were given at the beginning of the section. Where A sub 0 is the amount of uranium-235 initially present, so that's whatever you started with. A is the amount present after T millions of years. K is the decay rate. So it says the half-life of U-235 is about 700 million years. Use the information to calculate the value of the decay constant K for this model. Okay, let's do that, because this problem confuses people, because you actually have to go through and do the problem. You almost do the whole problem twice. Not quite, but you almost do. And a lot of times people think they're done after the first time through, but you aren't. So let me walk you through this. Okay, let's see. So we've got our A equals A sub 0 e to the negative kt. Okay, so let's see. What are we talking about here? They say the half-life of uranium-235 is about 700 million years. Use this information to calculate the decay, the value of the decay constant, K, for this model. So what is decay rate? When you're talking about half-life, it's kind of interesting. Half-life, we talked about, I kind of told you from a physics perspective why uranium is decaying down into things like lead and other types of things, right? So the half-life is the amount of time it takes some amount of uranium that you have collected together to become half as much. How long does it take it to decay into half? And it's a little bit strange because it doesn't matter how much you have. So if we take 1 gram of uranium and put it there, this says that 700 million years later we'll have half a gram. But what if we have a ton of uranium? Well, 700 million years later we'll have half a ton. So in one pile we only had half a gram decay, but in the other pile we had half a ton decay. That seems kind of weird, but it has to do with that way I described about how those nucleuses are breaking apart and the little protons and neutrons are hitting each other. Mostly the neutrons, I guess, because the protons are affected by charge. But the less of those atoms you have in a certain spot, the less of them you have breaking apart, causing that chain reaction. So half-life is actually independent of how much of it you have, which seems totally bizarre. Okay, so that's how half-life works. And they're telling us that the half-life is 700 million years. Use this information to calculate the decay rate. Okay, so let's fill in what we have and talk about how to do the rest. Okay, so we've got A equals A sub 0. That's, remember, A sub 0 is the initial amount, and A is the amount we end up with. Okay, then we've got E, and we're going to raise this to the negative kt. K is the thing we're looking for, and T is the amount of time it takes, in this case, for it to break into half as much stuff. It's the half-life. They're telling us in the problem that's 700 million years. If you're following along, this is on page 332, example 7. Okay, so then for T, we're going to put, instead of T, we're going to put 700. Because we're just going to use million years. We don't want to have to write all those zeros, right? So we'll just say 700 million years, knowing that we're talking about millions of years. Okay, but then it seems like we don't have enough information because we don't know how much we started with. But remember I said it doesn't matter how much we started with. The goal is that we end up with half as much. So actually we can play a little game here and say, well, then the amount we end up with should be 1/2 the amount we started with. See, we started with A sub 0, so we end up with 1/2 A sub 0. Now the cool thing about that is now we can divide both sides of this equation by A sub 0, and we get something a little bit simpler. 1/2 equals e to the negative k 700. And we go, oh man, we're trying to solve for k, but it's in the exponent. What am I supposed to do? Well, remember, that's that red flag I've been telling you about. That's when you know to bring in the logarithm. So what we're going to do is do the same thing, except take the logarithm of both sides. Natural log of 1/2 is equal to the natural log of e to the negative k 700. So we've got natural log of 1/2. Natural log and e undo each other. So we get this e and that undo each other. We end up with this. Divide by 700, and we're there, more or less, right? Divide by negative 700. So you end up with the natural log of 1/2 divided by negative 700 equals k. Throw that in your calculator, and you'll get about 0.00099. And then you have your decay value. So if we go back to that problem, actually, let's write the whole thing now, just to make it clear. So make sure everyone follows. Our final equation then is that A is equal to A sub 0 e to the let's put that in there, negative 0.00099 t. Okay, so right there. So that means if we're given a problem where we're given the initial amount and we're given an amount of time that it sits there, we can figure out how much we end up with. They have to give us those two pieces of information or we'll have insufficient information. Okay, so then what was part 2? So just to sort of clarify for everyone, we just did this first part A. The half-life of uranium-235 is about 700 million years. Use this information to calculate the value of the decay rate constant for this model. That's what we just did. Now we're going to use the model that we just constructed. Use the model with the newly calculated value of K to determine how many years it would take for a particular quantity of uranium-235 to decay to 90% of its original amount. Okay, so let's see. How would we write that? So let's do that part now. Okay, so we're going to play a same game here like we did where we did 1/2 the initial amount. This time we're going to do 90% the initial amount. So you'll see the steps are going to look very, very similar to what we just did. So we're going to take, let's see where we've got our problem. Except it's going to be 0.9 A sub 0, and we don't have 700 anymore. We now have T, but we do have K. We know is 0.00099. So it looks like this. So this is 90% of our initial amount. That's how we write it, 0.9. So 90% of the initial amount equals the initial amount raised to this model times t. We just took the thing right before it and plugged in this new part. Well, again, the a sub zeros cancel each other. That's great. So let's get rid of those. Okay, now we're going to take the natural log of both sides. Okay, we take the natural log of both sides of the equation. The natural log of e, those undo each other. So on the right, we get to simplify things really nicely by making this like that. So the natural log of 0.9 is equal to negative 0.00099t. Divide both sides by this value, and then you'll have your t, right? And then throw it in your calculator, and you'll get t is about 106.4 years. Okay, is how you do that problem. So let's move ahead. We have about 15 minutes left. Let's see what else we can get to. Here they have a piece of equipment depreciates according to this function. So here you could talk about like depreciation over time, right? Like when you buy an automobile, if you go to a car lot, buy a brand new automobile, that thing immediately like devalues itself as soon as you buy it. You haven't even put 100 miles on it. You've greatly decreased the value, because why would someone buy your version that you own when they could just buy a new one, right? Same thing happens with equipment. If you run a company, sometimes you can write off the depreciation of the stuff that you buy for your company. If it devalues, you know, first of all, that changes the value of your company, but also you can sometimes write that off as a loss. That's a way of sort of hiding taxes for profits that people use sometimes. So that's a problem you can do. And that kind of closes that one out. So then we get to 4.3. Now 4.3 and 4.4 have pretty extensive videos available to you. So make sure to watch those videos in Canvas. And then of course there's the videos that go along with each problem as well, each individual piece. Okay, so this is where we're talking about the derivative. So let's look at the derivative of these. Okay, differentiating the natural log function. Wait, did we skip? Wait a minute. Is this right? Seems out of order. Oh, that's okay. I guess I forgot. They do it in a weird order. They teach you exponential functions, then the logarithm. Then they teach you differentiating the logarithm and then differentiating the natural exponential function. Usually books do it in the different order. In fact, I'm going to show it to you in the different order, I think. Why is this making it so big? Because here is some great news. This is why I said that differentiating the exponential can be very convenient. The derivative of e to the x is e to the x. It is its own derivative. That's pretty convenient, right? You're doing a problem where you have to take the derivative of e to the x. Well, it's e to the x. It's just itself. It is its own derivative. This is one of the reasons why this is one of the many reasons why this is an extremely convenient function to use, right? Because it's its own derivative. So notice, like right here, they say find the derivative for this function, 8x cubed times e to the x. So let's see. Looking at that, what do I think when I look at that, right? Hopefully you're able to break this down in the way that I'm going through and working on it. Okay, actually, okay, sorry. We're gonna have to end about 10 minutes early today. Something just came up I have to go deal with. So we're gonna end 10 minutes early. I'm gonna pick up here later in the week. So on Wednesday, we'll talk about the the derivatives of logarithms and exponentials. Okay, so I'm going to close down the YouTube stream. Everything's fine, but I have to go take care of something that just occurred. So I'm closing.